Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the second lecture of this Magnetostatics chapter. So up until now we have learned about what is magnetic field intensity and magnetic field distribution for different type of configuration for a finite line conductor and a circular loop. Okay, those two things we have learned on the center as well as on the axis. So in today's lecture, what we'll study, we'll mainly study about magnetic force. Okay, so I will just rename this topic. We'll mainly study about how does a charge gets affected in the presence of a magnetic field. Like what does it feel? It feels a magnetic force, right? So we'll mainly discuss about magnetic force in this in today's lecture, and obviously we learn about the different type of configurations due to which I like that charge gets influenced due to a magnetic field. So first, just like a GK question, basic question. Okay, can you tell me that if I have is like circuit like this is just a simple, let's say, wire which has a resistor small r, okay, and a voltage source is connected in series. If some current is flowing through this, and if I place somehow I bring some charge from outside and bring this charge here, and it is at a distance r from this particular conductor, can you tell me what will be the force on this Q? Because there can be a electric field as well, right? Because there are charges here, there can be electric field, and there due to this current flowing there will be a magnetic field as well. So can you tell me what will be the force on this charge Q? Pause the video and just think. Okay, so now if you have paused the video and you have told me that there will be a force on this charge, which will be due to what? Which will be simply, just reduce the size, F, due to a electric field, right? Just hold on, I will just reduce the eraser size. Electric field. So I have an electric field here, okay, which is equals to Q into E. The E is getting generated here, and I will say you are actually wrong, and I was actually also wrong initially when I learned about this, right? Actually, the interesting fact is what will happen here is that as there is no stationary charge over here, charges are always moving, okay, there is no stationary charge, right? Current is flowing. What does it mean if current is flowing? So I is not equal to 0, correct? I is not equal to 0. Now I'll just change the shade of this. Can I change it? Okay, I cannot. If I is not equal to 0, that means what? dq upon dt is not equals to 0. So charges are not stationary here. Okay, so this is not like that configuration where I had a line charge of uniform line charge density, right? Where I had a wire of uniform line charge density. It is not that case. Their charges were stationary, plus q charges were stationary at the surface. But here it is not stationary. Charges are constantly moving. So if charge is constantly moving, right, what will happen? The net electric field here, right? The net charge inside this will be simply Q net. Will be simply 0. Why? Because dq by dt is 0. So whatever charge is coming in, it is going out instantaneously. So if Q net is 0, that means my E net, right, electric field, will be 0. So electric field is 0. That means the force due to electric field on the charge, on this particular charge Q that is lying here, will be simply 0. Force due to electric field will be 0. There will not be any force due to the electric field, because there is no electric field. Due to this particular conductor, there is no force due to the electrostatic nature, but there is a force due to the magnetostatic nature. Why? Because my magnetic field is not equal to 0, because I know that if a current flows, right, if a current flows, the magnetic field is what? Magnetic field is simply mu naught I by 4 pi r cos alpha plus cos beta, whatever the direction be. Okay, I will come to the direction, don't worry about that, whatever the direction is. But the most important point is the magnetic field is not 0, the electric field is definitely 0. Okay, so you have to understand these two things. So now what I wanted to tell is what is the force due to this magnetic field. I understood that there is no electric field. Okay, so it will not get any force. But what is the force due to the magnetic field, right? I want to reiterate it again. please don't get confused this with this configuration that I had a uniform line charge density of lambda, and the electric field due to that same line charge was simply E equals to, please go back to your notes, it was 2k lambda upon pi by r, right? This was the and by a rho cap. But this won't be the case here, because here this charge was stationary. This lambda charge was stationary. But now what is happening? This is not charge, right? Current is flowing. So charge is always moving. Okay. So net charge is 0. That's why Q net will be simply 0. Okay. So through this I can say Q net is equals to 0. Hence electric field is 0. So I'm just reiterating it again so that you will be able to understand it. So that thing is established. The electric field due to the wire is 0, but the magnetic field is not 0. That I just told you. Magnetic field is this particular value. So what will be the force generated due to the magnetic field? Okay. So the force generated due to the magnetic field will be FB. The formula, like it is experiment. We have found it out experimentally. Like I don't have any derivation for it. It is Q. That is the magnitude of charge cross V cos B. What is the V? V is the velocity of the charge. If this charge is stationary, right, there will not be any force. So here, if I would have asked you, I have just placed the charge over here, Q. What will be the net force on this charge? It will be 0. 0 due to the, as electric field is 0, okay, reason 1. Reason 2, due to the magnetic field, although magnetic field is not 0, but velocity of the charge is 0. Hence, overall the force on the charge, if it is on rest, right, it will be simply 0. So I've written here a few points. We can read this point. So what is this telling us? A moving charge generates both electric and magnetic field. Okay. A stationary charge experiences no magnetic force, as the magnetic force acts only on moving charges. So a moving charge actually will generate both electric and magnetic field, but here as it is the net charge here is 0, so electric field net will be 0. Okay. Net electric field will be 0, but if a charge is moving, right, it will generate both electric and magnetic field if a single charge is moving. But here multiple charges are moving, so overall net electric field is 0. But here I am talking about a single charge in isolation. A stationary charge, as mentioned, experiences no magnetic force, as the magnetic force acts only on moving charges. This has been found out experimentally. Okay. A wire carrying a steady state current is electrically neutral. Why? Because net charge will be 0 and does not produce an electric field. As it is electrically neutral, net charge is 0, hence it does not produce electric field, but it does generate a magnetic field. It does generate a magnetic field, but as the velocity of this Q charge, right, is 0, it is not moving, hence the force due to the magnetic field will also be 0. Okay, these few key, things you should know, because they can ask you question theoretically, conceptually. Okay, so this we have understood. Okay, but now what if I tell you that, okay, this charge Q is now moving with a velocity V? What will be the net force on this? So if V is not 0, right, now not null vector, then what will happen? Then I can say the force due to the electric field is 0 simply, but net force on the charge Q, right, will be due to the magnetic field, and it has been experimentally found out that it is equals to Q times V cross B. Okay, this is just simple Q scalar multiplication, and this is V cross B. This is the cross product of two vectors. So here, like, the same thing is written, like this has been found out experimentally, that a charge moving in a magnetic field experiences a force that is not due to an electric field, it will be due to a magnetic field. Okay, if it is moving across a wire. So this has been experimentally determined. Now just one key point I wanted to tell you, you have to take care of this sign Q. So if this Q is positive, then force will be on the same direction as the direction of V cross V. I hope you understand how to do V cross V. I will show you just in the next slide. And if the Q is less than, so it will be same direction, and it will be, if Q is less than 0, it will be opposite direction. What opposite direction? Opposite direction meaning whatever vector I will get after doing the cross product of V cross B, it will be opposite, because negative sign is there, it will just be the opposite of that. Where do you get confused? In electrons, because electrons have negative charges, and here you write Q, but you forget to write the negative sign, and instead of the direction being west, it should be east, and you have made a mistake, and in the option west, east, both directions will be there, and you will like choose the wrong option. So you have to be careful. Now from this particular diagram, can you tell me what is the direction of force acting on this electron? So I can observe the magnetic field is going inside, right? Magnetic field is going inside. Again, I will use the same simple right hand rule. Okay, right hand rule. So magnetic field is going inside, but I have to do V cross B. So let's assume that the velocity of this particular electron is along this tangent, right? Along this direction. Okay. So V is in this direction, and then I will do cross. Then I will curl my fingers towards the magnetic field. If I curl my fingers towards the magnetic field, what do I observe? I observe it's something on this side, along this side, right? Along this side. Again, if I am at this particular region, my what will be the direction of the force? It will be again V cross V. So V is in this direction and force is along this region. So it is always radially outwards. Okay. It is always radially outwards. Like what is happening? It is always perpendicular to my velocity vector. It will be always perpendicular to my velocity vector. So actually, if you observe, my displacement is where and my force both are perpendicular to each other. So will any real work happen? So basically, whatever force vector I will get, right? The vector F will always be mutually perpendicular to V velocity and my B. That is the definition of cross product. It gives me a vector that is both perpendicular to V and B. That is the definition of a cross product. So if I get a vector that is perpendicular, so that means my force is perpendicular to both velocity and B. If it is perpendicular to velocity, it means my force is perpendicular to displacement as well, right? ds vector. And what is the work done? What is the work done formula? So the work done formula, dw, this is a scalar quantity, equals to f dot ds. If you remember, small work done, right? F dot ds means what? F ds cos theta. Cos theta is cos 90 because they are perpendicular. So this will simply be 0. So actually, this you should know, and this can come as a statement question. Magnetic force does no real work on the charge. Okay, it will never do some real work because it can never change the direction of this particular object, of this charge. It doesn't have the capability to do. Okay, it doesn't have the strength. Electric field had that. What was electric field force? It was Fe equals to QE. So whatever the direction of electric field, in that direction this charge will get deflected. We have more questions, examples as well. But magnetic field, the interesting fact about magnetic field is that it can never change the direction of this electron. Wherever in which direction it is moving, it will keep on moving there, but it will apply a force that will be perpendicular. Okay, so yeah, so basically its f dot ds will be 0, work done will be simply 0. Okay, that thing is pretty important. And if you observe, your force depends on three things. One is the velocity. If charge is at rest, there will be no force. If there is no magnetic field, there will be no force. If the charge itself is 0, let's say it's a neutron. So in neutron, no force acts, no magnetic field will act. Okay, no magnetic force will act. So these are the few things that you should know. So now we'll talk about cross product. So cross product you'll already know. I'll just revise quickly. How do you find out the cross product? If I have two vectors A and B. So first you place vectors A and B tail to tail. You place them tail to tail. Okay, that's how you find out the cross product. Place them tail to tail. Then what do? You place your fingers along the A vector, right? Curl your fingers from A to B. Okay, first you start from A and then curl your fingers from A to B. So you have to place your fingers from A to B. During that axis case as well, during the previous lecture, during the derivation, I skipped that portion. How you used to find out your cross product. So here, so during this derivation, right, I will just quickly go through here. Okay, how you used to find out the direction basically. So I have a dl vector here and I have a r vector here. So they are connected tail to tail. Currently they are connected tail to tail. So this is the r vector and this is the dl vector, right? I have to find out dl cross r. So how will you find out DL cross R? DL cross R, I will place my DL along the fingers and curl it towards the R, right? So it will be somewhere in this direction. Somewhere in this direction, correct? Now I will do the same thing here as well. This is my DL vector, okay, and this is my R vector, right? This is my R vector. So I will start with DL and then this is my DL vector and this is my R vector, correct? So I will start from the bottom DL and then curl it. Okay, so it will be somewhere in this direction, right? Somewhere in this direction. So I didn't derive it properly there, so I'll just quickly do this here. So it was in this direction, correct? So overall the same thing, that the sine components, if this is theta, right, if this is theta, the sine components will get cancelled, the cos components will be left. Okay, so exactly that is what is happening. So if we do the same thing here as well, this is DL, this is R. So I'll do the DL cross R. If I do the DL cross R, DL is in this direction, and just use your right hand. DL is in this direction, and I will do that R. So DL cross R. So it will be something like this, DL cross R. So it's something like this. It's somewhere here, and on the opposite as well, it will be in this direction and in this direction. So it will be something like this. So theta will get cancelled basically. So I hope you get the point. So that is why I wanted to emphasize, because previous lecture I didn't explain the cross product much well. So I hope you understand how do you find out cross product. Okay, so that thing is clear, right? And one thing is clear: magnetic field will always act in the perpendicular direction to the velocity. The force due to the magnetic field on the charge will always act in the perpendicular direction. Now there can be two perpendicular directions, negative, positive, right? This can be minus, plus. So that is understood. So we have to identify that according to the sign of the charge. That you have to keep in mind. So let's do a few questions so that the concept gets more clear. A negatively charged particle falling freely under gravity enters a region with a uniform horizontal magnetic field directed north. Okay, so I have, let's say I have this north, south, west, east, and I have a charge Q that is falling, right? That is falling like this, and it's negative, minus Q. Okay, I will just write it with the sign. It is minus Q, and magnetic field is directed towards north, so it will be like this, right? It is a uniform magnetic field in the horizontal direction. It will be directed like this. It will be from south to north. The particle will be deflected. So magnetic field can only deflect the particle, but will not change the velocity. The velocity won't change, right? Here if you observe, it can deflect it like initially it was here, it will change its direction, but the velocity, the magnitude won't change. Whatever the speed here, the same speed will be here. It cannot accelerate the particle. So I will write here one key point about magnetic fields. Okay, so what is the key point? Okay, that went bad. So just copy and paste this over here. So I will write here one key point about magnetic field is, this is the key characteristics, and please do listen to me here carefully, that magnetic field can change the direction of movement of a charged particle but it can never change the speed. Please do take care of the words that I am saying. Speed is a scalar quantity, so it will never change the speed of that particle. So speed won't get changed. Okay, here. So speed would never be able to change the speed. That's why there is no acceleration along the direction, and that's why there is no work done. It only changes the direction. So here what is happening is that this actually works in a circular motion basically. Like if you have studied circular motion, you will understand that here the force was in this direction. Okay. Then again, when it's in the perpendicular direction to its movement, so actually just the direction will get changed, and its speed, velocity won't get changed, because if this v gets changed, then everything will change, right? So if it is in rest, it will remain at rest, magnetic field won't do anything. If it is in velocity, its speed will remain at v, but it will just deflect the object, it will just deflect the particle, its direction will get changed. So here we'll observe with this live example here. Okay, so the particle will be deflected towards what? So here it is, the velocity of it is in the downward direction, right? Because it has some mass, so gravitational force will be working, right? So as it has some mass, so gravitational force will be working. So due to gravity, it will be falling down. Okay, it is falling down. Fine, it is falling down. Now this is the direction of the velocity, right? And what is the magnetic field? Magnetic field is inwards. Magnetic field is inverse, going into the screen, right? If south is towards me, north is into the screen, so magnetic field will be inwards. So magnetic field is perpendicular, just like this. I will just show you. Okay, this is not like this. This one go away. Fine. Magnetic field will be something like this. Okay, and it is perpendicular because it is downwards and it is in the north direction straight. Like this is one of the direction of the velocity of the particular charged particle, and this is the direction of the magnetic field. So it is going towards you, coming towards you, right? This is direction, and they are perpendicular to each other. They are perpendicular to each other. But where will the charge get deflected? So I will do V cross B. So V is here. So I cannot like show you directly. It is downwards, and I will cross it towards here, right? And my thumb will show the direction. So this is downwards. Then I'm curling it, and I'm seeing right hand, right? I'm seeing towards the right, this direction. So I'll start from V velocity inside down, and then curl my fingers along the B vector, and then I am observing my thumb direction. That thumb direction is simply on the right hand side, simply along this right hand side, right? This right hand side. What direction it is? It is eastward, right? So this will be simply towards east, and you will mark your option A, and you will be wrong. Okay, why you will be wrong? Because I told you, right? I warned you. You have to take care of the sign. So you did the cross product. So this is my velocity. This is my magnetic field. You did the cross product and you got this vector, right? So which is the vector along the direction of V cross B. So I got this vector along V cross B. But what went wrong? The force expression was actually equals to Q times V cross B, and here in our case it is minus Q. So whatever direction I got for V cross B, I had to just flip it. It will be anti-parallel. It will be 180 degrees, right? So it will be flipped. So obviously, as the cross product was this, but it will be flipped. So I have to apply a negative sign. So it will be this, right? This. So obviously, it is westward. So it will be west. It won't change the velocity, but obviously it will change the direction. Okay. So that's the important point that I wanted to go about. So it will be westward. Okay, so this is one interesting fact, and like in GATE also they gave few interesting questions. So we have a 1 coulomb of point charge moving with a uniform velocity 10 ax. So the velocity, like this is totally a numerical based question, so I will write down the data points. So velocity of the charge is 1 coulomb. The charge value is 1 coulomb. It is positive charge. Okay, and velocity of it is 10 ax cap meter per second, and it enters a region of x greater than 0 having a magnetic flux density this. So magnetic flux density is this, although it is not uniform, but we just have to do simple a v cross b, right? The magnetic force on the charge at x equal to 0 plus. What will be the magnetic force on the charge at x equal to 0 plus? So first of all, I have to identify the expression for magnetic force. So what will be the expression for magnetic force on that particular charge? It will be q times v cross b. Q is 1 coulomb. Okay. So we'll write this one only. V is 10 ax times b, 10y ax plus 10x. This will, okay, this is (10x). This was 10x, right? Ay 10a. So this will be equals to, okay, this board sometimes gets stuck. Okay, this will be Ay plus 10 az. Now if I do the simple cross product, what do I observe? So this ax cross ax is 0, sine 0. This will be ax cross ay, that will give me az 10x plus az, and ax cross az will give me minus ay, and 10 times 10 will give me minus 100 ay. Okay, so obviously they are asking me at x equals to 0 plus what will be the magnitude of the force. They are just asking the magnitude. Remember, they are asking the magnitude, right? So x is equal to 0 plus, around 0, this will be almost 0. So f at x equals to 0 plus, this term goes to 0, only this term is left, that is minus 100 ay, and they want me to write the magnitude. So magnitude of this particular thing at x equals to 0 plus will simply be 100 newtons. So 100 will be your answer. In this case, 100 will be your answer simply. Okay, this will be the answer. So yeah, I hope you understand this question. These are a simple question come. This also is a good question, and for some reason they gave MTA. I don't know why was what was the reason behind MTA. If you don't, if you know the reasoning behind this question giving them MTA, you can put down in the comments below. So here they are asking basically, I have a figure, and in this figure the electric field E is there in the AZ cap direction and B is there in the AX cap direction. Okay, they have mentioned this. And okay, I now understood what was the mistake here. Actually what happened was, here they have written electric field is in the x and z direction. Okay, but here actually it is the opposite way around. So that's where the mistake came. Actually they should have told here that this should have been, I will say this should have been actually, this should have been z and this should have been x, because electric field actually is in the z direction and magnetic field is in the positive x direction. Okay, so there they missed this point, and that's why I think they gave MTA. Else this question is very good. This question is very good, and have constant magnitude. So electric field and magnetic field both are constant. Okay, electric field is some E naught in the z direction, and magnetic field is in some, this is not vector, some B naught constant in the AX direction. Fine. A positive charge Q is released from rest at origin. So it is just placed here. A positive charge is placed at origin of Q. So Q is greater than 0. This is positive. Which of the following statements is /R true? Which of the following statements is /R true? So which of this will be true? The charge will move in this direction. The charge will always move in this direction. The charge directive will be this. The charge will progress in direction. So they are just talking about direction. So I will directly find out the direction. Now there is electric field here. So if there is electric field, the charge will actually experience a force due to the electric field. And what will be that force? That force due to the electric field will be simply Q times E. Okay, so it is simply Q E naught in the EZ cap direction. So it is experiencing a force in the positive EZ cap direction, because this charge will get attracted to the electric field. It will go along the electric field direction. Okay, fine. But is there any other force as well? There is another force as well, right? What is the other force? Other force is F B equals to what? FB is equals to Q V cross B. Okay, so what will be the direction of the velocity vector? So here from here itself I can say that the direction of the velocity vector will be some V naught. It will be a function of time actually, V of t in the AZ cap direction, because the electric field is telling it to move in the AZ cap direction only. So it will be some V of t AZ cap. So I can derive this further. Like I will show you how to write without mathematical things. Just do it by visualization. I will tell you that as well. Just for now, I'm just deriving things here. So this will be Q V cross V. Q is there positive. V is in the V of t plus AZ cap direction. And what is the direction of B? Direction of B, right, is in the AX cap direction, right? AX cap. So it will be plus AX cap direction, okay, into B naught basically. So this AZ cross AX becomes what? AY. So this will be Q V of t B naught AY cap. Okay. So here it is telling me that the magnetic field is providing it some force in the AY cap direction. So there is no force in the AX cap direction. So it has only force in the AY and AZ cap direction. So my overall force will be in the, this will be V of t, this will be what? Q of E naught into AZ cap direction plus Q of V of t into B naught into AY cap direction. Okay, so from here what I can say that the particle is only moving in the AZ and AY cap direction. There are no other components, so it will only move in the ZY plane. Okay, so or YZ plane. The charge will always move on the YZ plane. So option B will be correct. Okay, and there is no trick. Option B will be correct. That is the correct option. Okay. So I told you like you can do this mathematically, but how can I do this without mathematically? And you might have one question coming into your mind that, sir, you said magnetic field does not change any velocity. So here the velocity can get changed, right? Because the magnitude is changing. But no, here this particular component is not changing its velocity. Okay, this is not changing its velocity. This is actually changing its velocity. What this component is doing in isolation, a magnetic field, what it does is it just applies a force in the perpendicular direction. Okay, that is what it is doing. So here the actual force is acting in the AZ cap direction, and magnetic field is just applying the force according to that particular velocity at that particular point. So the reason here is electric field is also present. That's why I'm getting this component. Okay, so magnetic field in isolation does not do any work. If you do F dot D due to only magnetic field, it always acts in the perpendicular direction. That's present inbuilt in the equation itself. V cross B means a vector that is perpendicular to both V and B. So it is always perpendicular to the velocity, always. So it doesn't do any real work. It doesn't do any real work. Okay. So that is point one. Point two, this was the method one. But what if you told me, sir, I don't want to solve like this. I just want to directly visualize and directly do without writing anything. So just put your pen down and try to understand with me. Okay, I will obviously not put my pen down. You have to put your pen down. So what is happening? So I have two fields, electric field, magnetic field. I know electric field will always the force on this charge on the electric field will always be along the electric field direction, as it is a positive. If it was negative, it would have been in the opposite direction, minus AZ cap. So point one, electric field will act in the plus AZ cap. So the force on this Q will act in the plus AZ cap direction, and this charge will start moving in the positive AZ cap direction. Okay, charge starts moving in the positive AZ cap direction. So when the charge starts moving in the positive AZ cap direction, then what happens? It has a velocity. Initially, it didn't have any velocity. As the charge keeps on moving, as it is getting accelerated, as it has a force. So acceleration equals what? Force equals to ma, and acceleration gives me some velocity. Velocity increases, right? So velocity keeps on increasing, and due to that velocity, in the presence of this magnetic field, this charge will feel a magnetic force. And what is the direction of the force? The direction of the force will be perpendicular to the direction from the velocity and the magnetic field. So magnetic velocity is in AZ cap direction and magnetic field is in this direction. So I will do V cross B. I will come here. I will do V cross B. If I do V cross B, I will get a vector on this direction plus AY cap. Okay, just do V cross B. Okay, I will get a vector perpendicular to both of them, as it is mutually perpendicular on this AY cap direction. So I will get a AY cap direction vector. So yeah, magnetic field will act in the AY cap, electric field will act in the AZ cap. So overall my particle will get deflected somewhere in this plane. It will always lie in the YZ plane. There will not be any force in the X cap direction. So that's why option B will be correct. The charge will always move in the YZ plane only. It will not ever come to X direction. X will be always be equals to 0. Let's read the other options as well. The charge will move in the direction of Z with constant velocity. Velocity won't be constant because there is some force acting due to the electric field, and as I will just write here as the electric field, there is force, so velocity will keep on increasing. As force means acceleration, acceleration means velocity keeps on increasing, so velocity will not be constant. The trajectory of the charge will be a circle. No, right here I cannot comment how the trajectory of the circle charge particle will be. It will definitely not be a circle. When it becomes a circle, when there is no electric field. If you observe here, when there is no electric field, right, what will happen? This charge particle will always experience a force. This is my V and this is my inside is my B, right? So it will always experience a force perpendicular to V. Always experience a force perpendicular to V. And when is the force acts perpendicular to V, it means it is getting some centripetal force, okay, which is radially outwards from the center of this circular motion. So it will act like a circular motion, and that will be a circular trajectory. So remember, when I get this circular motion, when electric field is 0, okay, so then the force due to magnetic field always acts in the perpendicular direction. So when does this happen? This is also an important point that you should know. Is trajectory will be circle when electric field is 0 and magnetic field is non-zero, and obviously velocity is also non-zero, okay, then only I will get a circle. Okay, this is simple physics, simple maths, right? I hope you understand this point. The charge will progress in the direction of y. No, right, it will progress in the direction of y, correct, but it will also progress in the direction of z as well. So it will be in the direction of yz plane. Okay, so this is also wrong. So I hope you get this point, and this question is very good. So in detail I try to explain you this question. Let's do few more basic questions. Let's do this question. What is the direction of the magnetic force on a negatively charged particle moving in a magnetic field? So this charge is actually negatively charged. So this charge is negative. Okay, so this is the first point that you should like write down. Okay, charge is negative. Don't make this silly mistake. Next, what is the direction of the force that will act in this negatively charged particle? So magnetic field is like by this dot. What this means? It means magnetic field is towards me. So magnetic field is towards me and velocity vector is top. So velocity vector is top and magnetic field is towards me, right? So I will do what? V cross V. So I will curl my fingers, place my fingers along the V, and then curl my fingers towards. I will go towards the velocity, the magnetic field, and I'm observing. I'm getting a force on the right hand side. Okay, getting a force on the right hand side. So I will observe a force on the right hand side. But will it be the correct force? No, right? It will not be the correct. It will be left, right? It will be left. Why it will be left? Because charge is negative. So it will be just the opposite direction. So here option B will be correct. Okay. So I hope you understood this point. How am I doing the V cross B? Okay. So let's do this again. This question: magnetic field B. This is uniform. Now this is only valid for uniform magnetic field. For non-uniform magnetic field, there are other things. Okay. Just for now, we will study uniform magnetic fields. A magnetic field, this exists in the space directed vertically downwards. Okay, this is directed towards the earth vertically downwards. A proton is projected northward. So again, I will draw the north, south, all those things. So this is north, south, west, east, and magnetic field is actually coming downwards. Okay, this is the plane basically. Magnetic field is coming downwards. Is projected northward at a speed of 3 into 10 raised to power 6 meter per second. So this proton is moving from south to north with a speed of 3 into 10 raised to power 6 meter per second. Okay, the direction of movement of the proton is here. Magnetic field is working in this direction. What is the force acting on? Now proton. What do you know about proton? Proton has a positive charge, right? So proton Q means greater than 0. It is positively charged. So I will just place my fingers again. So magnetic field is acting downwards and velocity is in this direction, not direction, right? Going towards you, going out of the screen. So again I will do V cross V. V is this, and I will do V cross V. I will curl my fingers in downwards, and I am observing in the leftward. I am observing a force in the leftward. This is the north direction. So this is on the left of the north. Left of the north is simply west. Okay. And this is a positive charge. So just hold on, Q is greater than 0, right? Yeah, this is vertically downward. V cross B is vertically downward, and I have a proton is projected northward. So it is projected northward. So I have projected it northward. So velocity vector is northward, and I'm curling my fingers from velocity is this. Okay, velocity is this. Curling my fingers downwards. It is vertically down. Electric field is vertically down, so it will be left. It will be left. Left means it is westward. Okay, it is west. So it will be option A. Okay, just hold on. Option A. I hope you are able to do. Just need to do V cross B. That's it, right? Just you have to apply this V cross B. Now there can be two options. This one, this 4.8 and 9.8. How will you identify that? So you just do simple calculation, right? How do you do simple calculation? Just apply this V cross B. So what is V cross B here? So I will just write down everything vectorically. So B is downwards. B is downwards. B is downwards. So let me write the coordinate system, right? Okay. So if B is downwards, right, that means B has 2 into 10 raised to power minus 5 in the minus AZ cap direction, Tesla. What about the other things? Velocity is projected northward. So if it is northward, right, it is in the minus AX cap direction. So V is 3 into 10 raised to power 6 minus AX cap direction meter per second. So what I need to find out? I need to find out the force, because there is no electric field. So force will be simply Q V cross B. So Q is for a charged proton, it is 10 raised to power 1/6 10 raised to power minus 19 into V is how much? 3 into 10 raised to power 6, and this is 2 into 10 raised to power minus 5 into V cross B. So it will be AX cross AZ. So this will come out to be minus AY cap direction on the left hand side. So this comes out to be 3 into 2 5. This will be 5 into 1.6. 5 into 1.6 is simply 8. Okay, no, not 5 actually, sorry. This is 6 into 1.6, right? 6 into 1.6 is 9.6 into, this is 10 raised to power 1, so this will be 10 raised to power minus 18. Okay, yeah. So 9.6 into 10 raised to power minus 18 in the minus AY cap direction. So this AY cap represents, like, this is my east, this is my west, this is my north, this is my south, and this is top and this is bottom, right? So this represents west. So this will be westward. So 9.6 into 10 raised to power minus 18 westward. Okay, I hope you get the point. Now let's come to this point, that, like, how does it act? I've already told you, right? Whatever we see a uniform circular motion. So there will be few parameters for that circular motion. So whenever a charge is present, right, charge particle is present of Q, and it is moving with a velocity V, obviously the magnitude of the velocity I won't change. What do I will change? I will change the direction, because my force will be acting perpendicular. Here if I observe, which direction force will be acting? So here velocity is, let's say, top, okay, and electric field is magnetic field is what? Going into the plane. So it is like going away from me, like this. Again I will do V cross B. It is leftward, right? So force will be acting somewhere left. This is the magnetic field force. Okay, so what is happening? Basically it will do a circular motion, because here it force is acting here, then here the force will act here, then here force will act here. It will just do a simple circular motion, that's it. Okay, so what can I say is that, do you remember the circular motion? So this on isolation, if only magnetic field is acting on a charge moving with constant speed, because the speed should not change, then the trajectory will be a circular motion. Okay, so basically how will the trajectory be? So the trajectory, like here, the force here is this point. When the charge will reach here, this will be the velocity and this will be the force, right? It is always radially inwards or radially outwards, so it is like a circular motion. If it goes through a uniform circular motion, right? One thing we know about circular motion. What do we know about circular motion? The centripetal force formula. If you don't remember, just you have to revise the circular motion. Unfortunately, you have to take my word that the force due to a circular motion, right, Fc, if you remember correctly, it was equals to mv squared by r. What is this r? R is this radius of curvature. That is an important parameter for us. They can ask radius of curvature. So basically, radius means about the point where it will just do the uniform circular motion. So here I can derive few expressions. Okay, what I can derive is that simply, if I just equate this, right, what is Fc? Fc is the force acting on the charged particle. What is that? That is qv sine theta, right? And theta will always be 90 because it will always act in 90 degrees with respect to the charge, with respect to the velocity. So it will be q v b sine theta. Sine theta is 90 because it will always be perpendicular. It will always be in the perpendicular direction. But in our case, why it will be always in the perpendicular direction? Because velocity and the magnetic field will always act in the perpendicular, right? The angle between the velocity and the magnetic field will always be 90 degrees. That is the reason. So b sine 90, this will equals to my circular motion, that is m, the mass of the charged particle, okay, into velocity of the charged particle divided by the radius of curvature r. So from this I will be able to find out what will be the radius of curvature. Radius of curvature will be Vv will get cancelled. This will become m v by qv. Now this is a good formula. Don't need to remember. Just try to understand how I got this expression. That's the only thing I wanted to take away from this, right? Just try to understand how I derive this. This is known as what? This is known as the centripetal force, as it is going inwards. Okay, if it is pulling towards the center. If it is pulling away from the center, it is known as centrifugal force. Okay, so this is known as centripetal force, as it is pulling inwards the center. Centripetal force, that the name is not very important. We study in JEE days, so don't have to worry about that. Just this thing you have to understand, that the radius of curvature will be this. Now can you do a sanity check of this? So if I have no magnetic field, then what will happen? What will be the radius of curvature? If I have no magnetic field, that means my radius of curvature tends to infinity, which is correct, right? If it is moving in straight line, it should move in straight line. It should not change the direction of the particle, as there is no magnetic field present. So it will just move and that way. Okay, so it is correct. There is no radius of curvature. Radius of curvature is infinity because there is no radius of curvature. Now what if my velocity increases? If my velocity increases, the radius of curvature also increases. Why? Because it has, like, it will go more fast, right? It will go more fast, so radius of curvature will also increase, as magnetic field will take some time to change the direction. That is the reason, right? So yeah, that is the reason why radius of curvature increases. Good. If my magnetic field reduces, the radius of curvature increases, because the strength, right? Strength reduces, so that the strength of the changing of direction, as the strength of magnetic field reduces, the strength of changing of direction, because magnetic field, what it does, it simply changes the direction, so it won't be able to change the direction so easily, so smoothly, as the strength of the magnetic field itself has reduced. Charge itself has reduced, hence the strength also will reduce. And mass, if the mass is more, the radius of curvature is less. Why? Because there is more inertia to quickly go away, further away, so it will have more inertia, so it will just remain along this periphery. Okay, so just some intuitive things. It's okay if you could understand. You can skip this also. Okay, not that important, but try to understand. No need to remember this formula, how I derive this formula, how I equated this. That is the most important part. Okay, so let's do a few questions. So a charged particle with a mass m and charge q moves along a circular path of radius r perpendicular to a magnetic field b. Okay, so this moves perpendicular to the magnetic field b, and it has a mass m and charge q, moves along a circular path of radius r. Okay, so this is just the situation that they are talking about. Not perfect though. This is r, this is q and m. What is the time taken by the particle to complete one full revolution? What will be the time taken to complete one full revolution? So how does it complete one full revolution? So what is the distance that the particle needs to cover? The particle needs to cover a total distance of 2 pi r. And what is the velocity? They haven't told me, right? They haven't told me the velocity. Only this much amount of information I have. So what I know, if the particle is doing circular motion, I know that the FB, the circular motion force, will be equals to mv square by small r. R is the radius of this circle, right? That has been provided to me. So what is the force? Force is q vb sin 90, which is 1 equals to this is simple equals q vv equals to mv square by r. So my v comes out to be what? V comes out to be q rb by m. Now I need to cover this 2 pi r distance, this whole periphery, right? Because they have asked how much time will it take to complete a whole revolution. So what is a velocity, or like speed, magnitude of velocity? It is simply distance by time. So the distance is provided. I know the velocity. I just need to find out the time. So I will find out the time. So time will be equal to d, that is 2 pi r, divided by the velocity, that is q r b by m. So it will come out to be m will go at the top, r will get cancelled. So 2 pi m qb. So 2 pi m by b. Okay, 2 pi m by qb. 2 pi m by qb. Option C. Option C will be correct. Okay, here. So do you need to remember this thing? No, right? You don't need to remember this thing because this is also another formula, but this is not for the purpose of remembering, just for the purpose of understanding how am I deriving this expression, right? So this can be asked in question, okay, as a numerical type question, because they will provide you these values and then they will ask. But do you need to remember this formula? No, just remember this thing. How am I equating this thing? Okay, fc equals to mv square by r. That's it. That you need to remember, and that will be it. One interesting fact is, this is the time period, right? This is also known as the time period. And the interesting fact is, time period is actually independent of velocity. So this type of theoretical question can also get asked, that what does your time period depend on? Your time period definitely does not depend on velocity of the particular object with its what is moving. Okay, time period is independent of velocity. So it's an interesting fact that you should know. Okay, so now let's come to the next concept of this particular thing, that if I have a magnetic field, but that is not like spreading infinitely, right? We have finite amount of magnetic field. Let's say it is extending up to d. Okay, so what will happen? This particle, let's say q, is moving. Okay, sorry. This particle q is moving with a velocity of v in this direction. So what will happen? Due to this magnetic field, again I will apply v cross b. I will get some force about some radius of curvature, right? About some center radius of curvature. So what will happen? It will deflect at this point, then it will deflect at this point, and just at the edge, right? At the edge here, this is the edge where there is no magnetic field at the right hand side. So boundary of magnetic field. So after this, the magnetic field stops. So what, can you tell me what will happen when this particle reaches at this point? The velocity of this particle, right? When it reaches, let's say at this point, the velocity of this particle is something in this direction. Why is it in this direction? Because it has to be, like, if this is the radius of curvature, let's say this is the radius of curvature. Okay, that is a really bad example. Just take another color. Yeah, this is the radius of curvature, right? After this, what happens? The velocity, I'll just draw this properly. The velocity will be always perpendicular to the radius, right? Radius of curvature. It has to be always perpendicular. That's how the force works. So velocity vector is here, and with respect to the normal, right, this angle is theta. So actually, I want you to find out the value of this angle theta. How do you identify this value of angle theta? And how do you identify the condition for which this will actually deflect? When will this deflect? That also you have to understand. So this overall, this distance, right? This distance is d. Okay, the width of the magnetic field. And the radius of curvature is this r. Okay. Now obviously, for it to deflect, this d, right, has to be less than r. Only then the particle will go outside of the magnetic field. And in what direction it will move? It will move in the same direction which it was previously, this direction. Okay, it will move along with this trajectory, because here no magnetic field is present. As no magnetic field is present, the particle won't change its velocity, won't change its direction, nothing will change, no force will act. It will just move like according to Newton's third law, a particle remains in motion. Okay, it remains in the same motion as it was previously if no external force has been applied. Here is some external force has been applied. No, sorry, this is not Newton's third law. I think it was Newton's first law. I forgot. Okay, so if there is no external force here, right? If no external force is getting applied, so particle will move in the same trajectory as it was previously. Here, correctly, here it was correct that this particle was in presence of magnetic field. As it was presence of magnetic field, the force was acting radially inwards, so it was going in uniform circular motion. But at this point, just at this point, it went out of the magnetic field, so no force will act, and it will follow the linear motion. In which direction? In according to this velocity direction, right? In which it was previously. So this is r and this is d. I want you to find theta. Can you find out theta? So what will be theta? Theta here, if you observe, this is 90 and this is theta. So what will this angle be? This angle will be 90 minus theta, correct? If this angle is 90 minus theta, this is 90, right? This angle will be 90. Okay, this angle, like this is just a perpendicular, so this angle is 90 and this is 90 minus theta, so this angle will be what? This will be again theta. Correct, this angle will be theta. So if this angle is theta, how do I find out the relationship between r and d? So it will be sine theta or cos theta. What will be? It will be just hold on a second. This is r and this is theta, so this will be 90 minus theta. Okay, this is not a straight line actually, sorry. This angle, sorry about that, this angle, right, this angle is 90 minus theta actually. Yeah, I'm sorry, this is a straight line, right? This is just a straight line, so just a mistake, this is not theta. This angle, okay, this angle should be 90 minus theta. Why this angle should be 90 minus theta? Let's just look at this. This is a straight line, right? So let me name this angle as alpha for now, for no confusion. Alpha, okay? Alpha plus this 90 plus this theta should give me 180, because this is a straight line and I'm just adding all the angles. So I will write here alpha plus 90 plus theta should give me 180. So my alpha is equals to what? Alpha is equals to simply 90 minus theta. So this angle is 90 minus theta. That's why I told you that point of time it is 90 minus theta. Okay. So this is equals to 90 minus theta. So if this is 90 minus theta, just hold on. What will be this angle? This angle will also be 90 minus theta, correct? This angle will also be 90 minus theta. And this angle itself is what? This is just a perpendicular, right? If this is perpendicular, this angle will be 90. So again, if I add these two angles up, let me name this as beta angle. I'm just running out of colors now. Let me name beta. So this angle is 90, right? This is just a perpendicular. So alpha plus beta equals to 90. So if alpha plus beta equals to 90, then beta is equals to 90 minus alpha, which is equals to theta itself. So this angle beta is equals to simply theta. Okay. And what is sine of beta? What is sine of beta? So I can say from here, sine of beta or theta, right? It is same as theta only. Sine theta is equals to what? This is the hypotenuse and this is the altitude. It will be altitude upon hypotenuse, d upon r. Okay. And from here I will be able to identify the angle of this deflection. But do remember, this formula is only valid only when the d is less than r. Because the reasoning I just give you, if d is greater than r, what will happen? If d is greater than r, it will not ever go out of the magnetic field. It will always be in the magnetic field. If it is always in the magnetic field, so it will always follow a circular motion. But once if d is less than r, then only it goes out of the influence of magnetic field, and then only it follows the trajectory which it was at that end of this point, at this boundary. Okay, I hope you get this point. And I know the r. They will give you this d. I know the r. What is the r? R is simply this value, right? Just what you derived here, this value. So I will replace this mb by qb. So I will replace this r here. So my sine theta equals to d by mv by qb. So it becomes some formula dqb by mb. Now do you need to remember this? No, I'm writing this messy. Why? Because I don't want you to remember this. If I wanted you to remember, I would have written it perfectly inside a box and done that. I am writing it messy because I wanted to always derive, because it will take you 5 seconds to derive. Okay. And if you derive, you will also understand everything, right? In the examination hall, do you need to remember? No, you will always mess up. Some m will be top, v will be bottom. You will always mess up that. No need to mess up that. Just derive this, how I derived. Okay. Just try to understand the fundamentals. That's it. No need to remember this. Okay. Just derive from the force. Fc is equals to mv square bar. What is Fc? Fc is qvb. And from there, you will be able to find out r. And from the r, you will be able to find this sine theta. That is d by r. That's simply it. Okay. And you might think, sir, it is taking you so much time to derive. Yes, it is taking me so much time to derive because I am explaining, and this is I am doing only once. If I would have done it regularly, if I would have practiced enough, it will not take me much time. So that's why practice is very, very important. We are at the end stage now, and if you just keep on studying and don't practice, you will mess up your examination. Your examination will not go well. I can say it certainly right now itself if you don't practice enough. Okay. So that is the key point that I want to tell. Now let's do a few questions on this. Okay. So this question is very good. Pause the video and try to solve it yourself. Determine the angle of deviation. So this theta actually is known as the angle of deviation with respect to the this horizontal, right? With respect to this horizontal line. So determine the angle of deviation of a particle as it exits a magnetic field if the width d of the region if the width d of the region is if the width d is varying, if it is mv by 2 qb, if it is slightly smaller than mv by qb, if it is slightly larger than mv by qb, if the d is varying for this particular cases, tell me what will be the what do you say, angle of deviation. Okay, so let's solve it for the first case. So for the first case, they have given me the deviation is simply mv by 2 qb. Now will I apply the simple formula? You can apply the simple formula and you get your answer, but you have to understand this conceptually. Is this a valid d? Like, will the particle get deflected or it will always remain in circular motion? For that, I have to identify the radius of curvature. My radius of curvature must be greater than the distance of this magnetic field, width of this magnetic field, then only it will be deflected. So I will cross check that first. So what is my radius of curvature? Again, I will use the simple formula. What is the formula? QVB FC is equals to FC equals to MV square by R. So my QVB equals to MV square by R. So my R is MV by QB. which is correct? My R is actually greater than D, as it is R by 2. So R is equals to D is equals to R by 2. So D is less than R, so it will get deflected. Now you apply this formula. What is the formula? This one, if you remember, that's good. That sin theta will be D by R. It will just take you 30 seconds more to derive that, but it's good to remember. Or they will specify the deflection angle, right? They will actually specify, because here this question is bit off because they don't specify the deflection angle. So I will just show you here. I'll just specify the deflection angle. In the question they will tell you what do they define the deflection angle as. Don't worry, it will be either with respect to this horizontal axis or with respect to the normal axis, any of them. Okay, so here from whatever it is given in the question, I will write sin theta will be D by R, which is equals to 1 by 2. So theta will be simply 30 degrees. So I could have used a simple formula, that's fine, but you need to understand behind the scenes what is happening. Then only one day when the difficult question will come, you will be able to solve it. So this is pi by 6. So option A will be correct for the first one. Now let's solve it for the second one. Now when my width is slightly smaller than mv by qb, when my width is slightly smaller than mv by qb, then what will happen? So if my width is slightly smaller than mv by qb, mv by qb is what? Mv by qb is actually the radius of curvature. So I'll just copy this thing and I will just paste this in this page. Okay, so what I can say is that this is at the edge, right? Boundary of the particular magnetic field. Now this D is slightly smaller than this R. So what will happen? I will just reach at this point. And my charge Q, right, will be just outside the boundary. So what angle will it make? It will be just outside the boundary with respect to this D, because this D is almost equals to R, but just less than this. I will just be here, because here it is not an issue because D is greater than R. So once I will reach here, and then I will reach here, and then this D is just greater than the R, so it will just be outside the boundary. So in what is the direction now? The direction is simply in this direction, right? Perpendicular. It is not in this direction. Okay, it is in the top direction. So obviously the velocity is something like this. The charge particle will go like this. It will follow a quarter circle. Then this will be top. So it will be the angle with respect to the horizontal will simply be 90 degrees. So my angle here in this case theta will be 90. Okay, don't use the formula. Use your brain. Okay, if you use a formula, yes, you will get your answer. Here your answer will be what? Your answer will be simply, if you like use the formula, that D will almost be equals to R. So sin theta equals to D by R. So you will say 1. So theta equals to 90. So formula will work here, but it will not work in few cases, like the next case. So next case, if your D, right, is slightly larger than mv by qb. If it is slightly larger than mv by qb, then what will happen? And this time the arrangement is bit different. Now the particle was flowing in this direction. Can you tell me in which direction the particle is flowing? So you have to identify with the picture also, like in which direction the particle is going. Okay, so here if I just copy this thing, now what is the trajectory of this particle? So here magnetic field is coming towards me and velocity is on the right hand side. So I will just point my velocity and I will okay, this is my velocity and now it's coming toward me, it is downward. Okay, so the direction is something like this. The trajectory will be somewhat like this, right? Okay, and it has told me D is just about greater than R. So D is almost equals to R. So if D is almost equals to R, I will again use the same formula. Sin theta equals to D by R, almost equals to 1. So theta will be equals to again pi by 2, and your answer will be simply wrong. Why it will be wrong? Because you are using the formula, you are not using the concepts. So here your D is greater than R, so this formula is anyways not valid. it is only valid for d less than r. So if d is greater than r, what is happening? My particle will reach here and the boundary is here. I am still inside the magnetic field. So it will still flow in this direction. It will still go in this direction. Correct? It will still go in this direction. So if it is going in this direction, it will go, and it will be come out of the influence of the magnetic field. Right? It will come out of the influence of the magnetic field. So finally the particle will reach here, right? And then it will come out of the influence, because here there is no magnetic field, right? So the angle will be what? The angle will be, with respect to this axis, it will be totally 180 degrees. Correct? 180 degrees. So it was starting here, and this is the reference, and with respect to the reference, this is away from 180 degrees. So it will be 180 degrees. So your theta here will be simply pi. Okay? And these type of questions can come in the examination, and you have to understand that when to use what formula. Okay? So they can mention the reference in a better manner as well, but don't worry, we are just doing the question. When actual gate question will come, right, they will mention reference, everything they will mention. And I hope you understand that point, that this will do its circular motion, but at this point, right, again there is another end of magnetic field, and it will just go in the same direction it was going. Okay? So theta will be here pi. I hope you got the point. Now let's do a bit of derivation for force experienced by a current carrying wire under the influence of a magnetic field. Now this is not the force due to a current carrying wire. This is the force experienced on a current carrying wire under the influence of a uniform magnetic field. If it is under the influence of a uniform magnetic field, then what force will the current carrying wire experience? A current carrying wire also experiences a force. That force, fundamental thing we know, right? F is equals to Q into V cross B, and from that we will derive. Okay, so what do I know? I know that the charges here, whatever the charges are flowing, they have some velocity known as drift velocity. Each electron, each electron, net velocity of electrons is drift velocity. This much you know, right? This is the basic thing, and obviously we will not go too much in depth into the electrons and holes. So force will be equals to Q. What is Q here? Force on each electron. What is the force on each electron? It is minus E, right? Charge of each electron is E, negative sign, times V cross B. What is V? It is Vd. It is the drift velocity cross B. Okay? It will be drift velocity cross B. Okay? So this will be the force experienced due to a small electron, right? Small electron. Now what can I say? How much charge is actually going through a wire at a particular time? So I have a wire like this. How much charge is actually crossing through this, right? So this is a small volume, right? dV. I'm just zooming in the this current element. So this is small volume dV, and what will be the volume? Small volume of this, it will be A dl, right? Area is this area of this cross section. Cross section will be same. Cross section doesn't differ. Just this dl, small dl length. Okay. What is the area? Area is area. Okay, that's it. We will not go into area. It will be pi r square, but we are not going into that right now. Okay. So, but I just wanted to take the concept right now. Okay. So this is not an important, because other educators, they don't derive this. They just directly do it. I'm just still deriving you. So what is the amount of charge dq, small charge dq, that flows through this? Amount of small charge dq will be n e, that is the charge into the volume dv. Okay, which is equals to NEADL. Now what does this N is? N is the number of charges per unit volume. Okay, so if you multiply this number of charges into volume, I will get the total number of charges in that particular small volume, and if I multiply it with charge, obviously I will get the electronic charge. Okay, so total number of charges. Now, what is this equals to? This dq, if I put this here, right? Because this was a force on a small electron, right? This was force on a electron. So it is some small force df on a small electron. Now I want to identify force due to everything. So small force df, I will just replace this whole thing, right? This whole charge in a small volume dl. Okay? Charge in a small volume dl, I'll just replace this, because this was actually the sign of charge. This was a sign of dq. Okay, I needed to find out the amount of charge that was flowing through, and on that charge obviously this force will get act, this force will act. So I'll just replace dq with NEA VD, and NEA VD was obviously there here, and DL. Okay, so DL, what I did, DL is in the same direction as drift velocity, so I replace V with DL. Okay, because VD and DL are in the same direction. I'll say here VD and DL are in the same direction, because that is the direction flow of current, and that is the drift direction of the drift velocity as well. DL, why is this, are in same direction. Okay, so VD and DL are in same direction. Why am I doing this? I'm just taking out VD, I'm just keeping the vector here DL cross B. Why? To get to this format, and this format is known as what? Current. No need to remember this derivation, no need. Just I'm giving you a brief overview and just a visualization. Why is my small force I DL cross B? How does it come? That I want to explain. That's why I just derived, because this is not an important. Just main important portion is this. Small force, the small force on a current carrying element will be IDL cross B. What is this IDL? IDL is current element direction. This is known as current element. Okay, and the direction will be same as the current. Whatever the direction of current is, that is the direction of the current element IDL. Okay, what is DF? Magnetic force on small element DL. Okay, perpendicular to the current element. It will act on the perpendicular direction, because it will be DL cross B. So obviously it will be both perpendicular to DL and the magnetic field B. Okay, I hope you got this point. This formula you need to understand, and it's good to remember. Okay, it's good to remember. So how will I find out the whole force? What I will do, I will just simply do the integration. So if I just integrate the force, I will get back my whole force. It will be, I will be some constant value, I DL cross B. So I'll just integrate this I DL cross B, then I will get back my whole force on that whole conductor. So DL will be from L equals to 0 to L equals to some L. Okay, so we'll see all those things, don't worry. So let's do one basic question. Okay, a uniform magnetic field of 1.5 Tesla exists within a cylindrical region of radius 10 centimeter. So we have a uniform magnetic field of 1.5 Tesla that exists within a cylindrical region of radius this. So okay, well, I just need to write down the information. So B is 1.5 Tesla, radius like cylinder is here, exist within a cylinder of cylindrical region of radius 10 centimeter, aligned parallel to the axis from east to west. So east is here and west is here. So axis of the cylinder is something like this. Okay, and magnetic field is from east to west, 1.5 Tesla, and its radius of the cylinder R is 10 centimeter, or I can say 10 raised to power minus 1 meter. A wire carrying a current of 7 ampere in the direction north to south passes through this region. Like I have north is here and south is here. So I have a conductor that is carrying a current of 7 amperes from north to south. Determine the magnitude and direction of the force on the wire under the following conditions. Okay, so what are the following conditions? So first condition is if the wire intersects the axis. So if it intersects the axis, what will happen? It will totally go through this, right? It will totally go through this magnetic field. So the magnetic field will actually get cut in this. So what will be the force on the wire under the following conditions? So to find out the force on the wire, so what is my L vector? So this time L is straight, right? L is straight and L is constant. So I will just write down what is my small dl vector. Small dl vector is in which direction? So I will just write down the directions. Let's assume this as x. I'll just assume few directions, x, y, and this as z. Okay, so my current element direction is ideal is 7 in the dl minus a y cap direction. Okay, my magnetic field is in the direction of what? Magnetic field is in the direction of minus ax cap. So it is 1.5 Tesla minus ax cap direction. So will there be any force experienced if the wire, like the wire intersects the axis? So wire will intersect this axis, right? So there will be obviously be a force experience. What will be that force experience? So my small force dF is equals to I dl cross b. So I can integrate this whole thing. F will be simply IDL will be IDL or 7 times DL integration minus of AY cross minus of AX. Okay, L will be from 0 to, have they specified about the length of the particular? Okay, they have not specified the length. So I have written back the length. So length of the wire is supposed to be 0.2 meters. So I have just from the question I have read back. So the length is 0.2 meters. So what will happen? The limits will go from this 0 to 0.2, and obviously there is a magnetic field as well that I missed here. It should be B, cross B, right? So B has its own magnitude. It is 1.5. So obviously this will come out to be F 7 into 0.5 L going from 0 to 0.2 in what direction? AY cross AX. So it will be in minus AZ direction. Okay. F will be equals to minus this will be 7 into 1.5. So this will be 10.5 into 0.2, which will be 2.1 in the AZ cap direction, minus AZ cap direction. Why is this minus AZ cap direction? Like you can understand this intuitively as well, that here what is happening, it is going from north to south. So I am in the minus AY cap direction. My ideal is, current element is in the minus AY cap direction. Electric field is in the minus AX cap direction. Yeah, sorry for the interruption. Actually, a phone call came up. So what I was explaining was that the like this current ideal element is in the minus AY cap direction. So it is in this direction, and my magnetic field is in this direction. So I will place my hands along the ideal element, and I will curl my fingers towards this B, right? If I curl my fingers towards the finger, I am going into the plane. So it is going into the plane. That means it is in the minus AZ cap direction, whatever I got here as well. Minus AZ cap direction, same direction. Okay. So I have get the point for the first one. Let's solve it for the second thing. If I solve it for the second thing, what will happen? For the second case, what are they telling? They're telling the wire is rotated from the north-south direction. So from the north-south direction, it is rotated to the northeast-northwest direction. So northeast-northwest. What does northeast-northwest means? Northeast is somewhere here, and it will go towards northwest. Okay. So it is rotated 45 degrees. Okay, it is rotated 45 degrees. So initially it was in this AY cap direction. Now it is in the 45 degrees. What is this 45 degrees? In the same XY plane only. AX, this is what? This direction is what? This is minus AX minus AY, because this direction is in the negative XY plane, right? Negative XY plane. So now the direction has changed to, now the ideal element has a direction equals to 7 minus AX minus AY cap. I hope you understand what does northeast and south northwest means. Okay, I hope you get this point. Northeast northwest direction. Yeah, northeast to northwest. Correct. Rotated from the north south direction to northeast direction. Okay. It should not be northwest here actually. Only northeast direction. This should change. I'll just quickly change this. Northeast southwest orientation. because southwest is southwest is something like this. Okay, so it will be just tilted 45 degrees, okay. So what will be the angle? I will just show you. I will just copy this thing, okay, and I will show you what will be the actual angle now. The actual angle will be this. Okay, so this is the north to south, and it will be just 45 degrees. So can you tell me this direction? I have already given you a hint. This is the direction, right? In the minus ax and minus ay cap. If you just take the component of this, it will be same as x and y. So it will be minus ax and minus ay divided by the magnitude, obviously, because this we have to talk about a unit vector here. This will be divided by √2. Okay, so this is the magnitude. This is the direction. Now, can you do the same exercise? Can you do the same exercise that you have to find out the force? Okay, and it will be simply integration of I dl cross b from L equals to 0 to L equals to 0.2. Can you do the same thing for me? Okay, this is the homework for you. Can do it for me. So I have removed the third portion because third portion is like there is a bit of confusion on that. So I have removed that portion. That portion is like I need a full diagram, and the question from the book from which I got the question, like the full diagram, I didn't recall at that point of time. So I have just removed that portion. So there is another question. So let's try to solve this question. So we have a circular loop of radius r carries a constant. Okay, this of radius, circular loop of radius. This should be r actually. Radius r, and which carries a constant current of I. It carries a constant current of I. So we have a circular loop of radius r, and it carries a constant current of I. It is placed in a uniform magnetic field BO, with BO being perpendicular to the plane of the loop. So it is always in either inwards or outwards from the loop. What is the magnetic force acting on the loop? Now, can you what will be the magnetic force acting on the loop? So here this current is flowing, right? And magnetic field is always perpendicular. So it is like this, either cross or dot. I can take any assumption. So I will take cross only. So what will be the force acting on this loop? So what I can observe is that here what is the direction of dl, ideal element? So I can take help of this, is as this is circular, I can take help of cylindrical coordinate system. So my ideal element will have a direction of what? So I will take it to the next page. Ideal element will have a direction of I dl. If I assume this as the plane of xy, right? If I assume this plane as xy, I'll just, they haven't mentioned any reference, but so I have to take a reference. The reference will be, this is x, this is y. So this is in the a phi direction. Okay, so I will just assume for my convenience anti-clockwise I current. Okay, so this will be simply in the a phi direction, right? Ideal a phi. Okay, so this is one thing. And what is the direction of the magnetic field B? So B, I can assume it to be like in this coming towards me or outside. So I will assume it to be in the outward or inside, right? It is in the minus AZ cap direction, whatever you choose. So B I have assumed to be some uniform magnetic field B naught AZ cap direction, okay, or minus AZ cap, because I have assumed it to be in going into the plane. Okay, now they're asking me what is the magnetic force acting on the plane. What is the magnetic force acting on the loop? So how do I compute that? So simply what you have to compute is, you can say for here that your small force dF will be I dl cross B. So your net force will be what? I will be outside, integration dl is what? Dl a phi cross B naught minus AZ, correct? And how, like along what length you are going? you're following this whole path. So your length is from 0 to 2 pi small r, 0 to 2 pi small r. So like what is if I will just quickly do this. A rho a phi az. So this will be a rho cross az. A rho cross az is a phi cross az is a rho. So this will be I dl. This will be a rho. A rho is constant. Rho is not changing, right? Rho is not changing. So rho will be constant. This will come outside, and there is a minus sign as well. There is a minus sign as well. So it will be minus a rho. Minus a rho. 0 to 2 pi r. So this will, and b naught is there, right? B naught we cannot forget, it is constant. So this will be minus b naught I into 2 pi r in the minus arrow direction, right? So force will be somewhere net outward, right? In the arrow direction, force will be somewhat like this. Okay, it will always act in perpendicular direction to this current, and it will be 2 pi ir. Okay, the magnitude, what is the magnetic force? Net magnitude will be 2 pi ir. Okay, so direction they haven't told us, so we won't check the direction. We'll just quickly compute the whole magnitude. Okay, so yeah, this will be the case here. Is everything here correct? Just I'm checking once. Yeah, dl is varying like that, or you can write here dl instead of dl. You can write r d theta or r d phi, and you can vary your phi from 0 to 2 pi. Okay, that also you can do, whichever one suits you. Okay, so yeah, that's basically it for this question. So there is the last concept, that is, this concept is about the force between two current carrying conductors, two parallel lines. Okay, so if you have two parallel lines, what will be the force between them? So obviously this line current carrying conductor can't have a force on itself, just like a charge can't apply a force on itself due to its own electric field. If I have a plus q here, a minus q here, due to this minus q, this plus q charge will experience a force. Due to this plus q, this minus q will experience a force. But this minus q won't experience a force due to itself. That is not possible. The same concept I will apply here. I have two wires. Both the two wires will actually generate a magnetic field. What was the type of magnetic field? Like this, right? If you remember, it was circular loops. Okay, the first lecture we derived the expression. Now if I have two infinite lines, and the magnetic field generated by this particular current carrying wire, due to this magnetic field, a force will be applied in this second wire, right? So now this force will be applied here. So if this force is applied, so obviously it will either attract or repel the current carrying wire, and that is, we just want to find out the magnitude of that force. So how do I find out the magnitude of the force? Just by simply identifying the magnetic field and the IDL. So df I know is equals to IDL cross B. So what is the magnetic field produced due to this current carrying wire? It is magnetic field B1 will be simply mu I by 2 pi d, right? The perpendicular distance. This we derive in the lecture 1. Mu I1. Okay, the current due to the I1. What is the direction? For now I can ignore the direction. Okay, but here if you understand, this is going into the plane. Okay, if I just curl my fingers, this is going into the plane. So this will be going into the plane. Okay, this is going inwards to the plane. That is fine. Now I need to find out the force in this. What is the force? Force will be this, right? So I'll just replace B1 here, and I will replace IDL with I2 DL. So in what direction I2 is? I2 is, let's assume I2 is in the plus. I will assume a reference for now. This is nothing fixed. My reference is this, right? Let's assume this as x, this as y, this as z. So if it is inwards, so this will be in the minus az cap direction. Okay, and this I2 is in the plus ay cap direction, right? So I can write small current element I2 dl equals to I2 dl ay cap direction. Okay, so I will just replace all these things over here. So what will be my force? Small force df. small force df will be I2 dl ay cross mu I1 2 pi d minus az. So what is ay az? It is plus ax, but as it is in the negative x direction, negative, so it will be leftward. So this current will actually, due to this current, this will attract this particular conductor, right? This, due to this current flowing through this conductor, this conductor will actually attract the other conductor. Okay, as I1 and I2 both are in same direction. Okay, we'll understand about this as well. Okay, so force, this is what, this is equals to what? So this small force, actually if I just write down properly, if the lengths are both L, okay, I will just integrate this properly. If I just integrate this from 0 to L, what will I get? What will the final expression? The final expression will be F will be equals to mu I1 I2 into L divided by 2 pi d, because like let's assume this length as L. Okay, this will be 2 pi d in the minus ax cap direction for now, but I am mainly concerned with the magnitude. I will talk about the sign later on. Okay, so this is the expression basically. This is what? This is F21. What does F21 means? What does F21 means? I will just do one thing, reduce the size of all of this. F21 basically means that force on second wire due to first wire, and the magnitude will be same. If you derive force in the first wire due to the second wire, magnitude will get same, but the direction will be different. F12 will be in the plus x cap direction. So both of these will be attractive in nature. Both the force will be in attractive nature. Okay, so this is the derivation basically, and this is the formula. So if you remember this formula, good, but you can always, like, it will take you hardly 20 seconds to derive this formula as well. You can remember that. And one more important point is that from this expression, right, if I just divide by dl on both sides, what will happen? I will get I2 mu I2 I1 by 2 pi d, and that is equals to what? That is the force per unit length. So that is also an important parameter. If you want to, if they ask in the examination what is the force per unit length, you will say it is mu I1 I2 by 2 pi d. So I will just derive this generalized term. This will not be mu naught. So so that we don't need the length, this how much length these wires have, we don't need that. We just need to know these parameters, mu I1 I2 by 2 pi d. This parameter is very good if engineers want to calculate what is the force between the two current carrying wires due to magnetic field. Okay, so this will be the case here. So another important point is the sign. So how do you identify the sign? So what do you do? If both the currents are in the same direction, then it will be of attractive in nature. Okay, if both the currents are in opposite direction, it will be of repulsive. Now you will say, sir, I am not able to remember this. Fine, then you have to derive. How will you derive? You just first identify the magnetic field direction due to the first wire. Magnetic field direction is inwards. Okay, point 1. Then you identify the current direction or ideal direction of the second wire. It is top. So top, then inwards. Then you top, then inwards. This is top and this is inwards, right? So I will do the I will do what? Ideal cross B. So ideal cross B. Ideal cross B is leftwards. So it will be leftwards. Now you will say, sir, I don't want to do this as well. So then leave exam preparation. Okay, because like if you don't want to remember, now if you don't want to spend time how to derive, then there's no point, right? So you don't want to do anything. So what's the point? But here, if they're in opposite direction, let's derive it for the opposite direction as well. So if they're in opposite direction, now what is the magnetic field due to I1? It is again inwards. So magnetic field due to I1 is inwards, going into the screen. Then what is the current direction? Current direction is downwards, right? Ideal current element is downwards. So I will place my fingers along ideal element and then rotate along the magnetic field. Rotate along the magnetic field, I am getting rightwards. So it is repulsive. Both the force will be repulsive, right? That's why it is repulsive here. So it will take you 5 seconds to derive the direction, or if you want to remember, you can remember. Okay, so that's it. And this parameter you should know, force per unit length. Sometimes this can get asked in the question, so you should know what this parameter means, force per unit length. Okay, so that is one point I wanted to leave you with. So yeah, that's like basically there are a few things. This I wanted to give you as homework. This you try on yourself, and in the next lecture I will solve this particular question. Okay, this I wanted to give you as homework, this question. And there is another concept, between Lorentz force. Okay, so we'll understand about Lorentz force, just not too much into details, but we'll go through that. Basically what we have already learned that, okay, this is nothing new, we just already know. So whatever I've explained in this whole lecture, right, that is what it is summarizing. So basically it is telling the difference between electric force and magnetic force. So electric force, now let's talk about the direction. The magnetic force is always perpendicular to the magnetic field, whereas the electric force is collinear. That means either it will be anti-parallel or parallel. Why is that the case? Because my magnetic force is equals to what? Magnetic force FB is always equals to Q V cross B. So it is perpendicular to both velocity and magnetic field, so it will obviously be perpendicular. Okay, this has been explained multiple times in this lecture also, so I will not go much too in depth. But what is my electric field? Electric field is Q times E. Simply it's a scalar multiplication. It can be either positive multiplication or negative multiplication. So either it will be parallel or anti-parallel, 180 degrees apart. So that's why electric field is always along the direction, and magnetic field is always perpendicular to the direction. Now dependence on the motion. The magnetic field actually depends on the velocity of the charged particle. If the particle is at rest, there will be no force. If the particle is in motion, there will be a force. In contrast, the electric force QE is independent whether the charged particle is at rest or in motion. It does not depend on the motion of the charged particle. It is independent of that. Now effects on charged particle. What happens when electric force acts on a particle and a magnetic force acts on a particle? The electric field accelerates charged particles by changing their speed. So electric field actually changes the speed. Okay, because it gives a force, it gives the acceleration on the same direction, while the magnetic field deflects the charged particle without doing any work. Because like this I have explained in the starting of the lecture, magnetic field doesn't change speed, it changes velocity. Now you might say, sir, speed and velocity are different things. Yes, they are. Obviously we have learned in physics, right? This is a scalar quantity, and this is a vector quantity, right? So it will change its direction, so it will follow a uniform circular motion, right? So actually it does not do any real work, but it does change its direction. So that is what magnetic field does, and electric field changes its direction and speed, obviously. Okay, so yeah, that is the thing. In whatever direction electric field will be, in that direction the force will act. So the total force, like there is a name to it, we already, like I've already told you that what will be the total force. Basically it is known as a Lorentz force. When both that force acts on a charged particle, both electric and magnetic field, then it is known as Lorentz force. It is simply the vector sum of the two individual forces, Fe plus Fb. Okay, that's it. Nothing fancy here. So there is one question. This question I want to tell you how to solve this question. We have a positively charged particle which is moves along the q axis. Okay, moves along the z axis. This has initial velocity v, moves along the z axis, and a magnet while uniform electric and magnetic fields are present as shown. So they are both, the electric and magnetic field are both in the positive x direction. Okay, so they are asking me what type of motion will the particle exhibit. So can you tell me? So if the velocity is here, due to the electric field, the particle will move in this straight direction, right? Particle will move in this linear direction because electric field is in this direction. But due to the magnetic field will be V cross B. So V is at the top and B is here. Okay, B is here, V is at the top. So I'll just do V cross B. If I do V cross B, right? So this will be V cross B. Yeah, if I do V cross B, what do I get? It will be inwards, going into the plane. So the force is going into the plane. So what will happen is that it will move like something like this. Okay, it will follow a linear motion. and the force will be something like this, right? It will just be something like this. And if you couldn't understand, don't worry, just have to know that this concept actually exists, that if both electric and magnetic field are acting, okay, and velocity is here in this direction, then the deflection will be what? It can only deflect. Due to the electric field, it will be a linear motion on this direction, x direction, and due to the magnetic field, it will be a circular motion, right? So it will be just like a helical shape. So that's why the name suggests helical motion. So when circular motion happens, when only magnetic field is present. When straight line, it will follow straight line when only electric field is present, right? So I hope you get the point. And parabolic path, when both magnetic and electric field is present in some weird directions, then we get parabolic path. So just wanted to give you an idea of this, so that like you get the intuitive idea analysis of how does magnetic electric field acts according to different directions. Okay, so this question also is just a numerical based question. This question I wanted to give you as homework. Okay, and in the next lecture I'll solve all this question, and obviously we'll learn about the Ampere's law. Okay, so basically that's it for today's lecture. Until then, happy learning.